Variables. Variables are those quantities in change of which we are saying a process is undergoing. In thermodynamics, we categorize these variables by two, which are state variables and path variables. State variables are those variables whose change only depended on the initial and final position during the process. Some examples of state variables are pressure, volume, temperature, internal energy, entropy, gives free energy. Means in any process, in this case, in PV diagram we are showing a process starts initially at the point A and goes in path like this and finally reach at the same point B. That means in this process change in pressure is 0, change in volume is 0, change in temperature is 0, change in internal energy is 0. You got the point. I am saying that all the state variables change only depend on the initial and final position of the process. If we make a process whose initial and final positions are same, then there is no change in state variables. On the other hand, path variables are those change of which only depends on the path. That means initially if a process starts from a point A and undergoing the path like this and finally returns back at the initial point. That means initial and final positions are same. As we have seen previously that in case of state variables, if we make a process in which initial and final positions are same, then change in state variable is 0. And in this case, if we calculate the change, you will see that the change of these variables, change of path variables are not equal to 0. They give some finite value. Examples of this type of variables are heat, work done. Here I am saying thermodynamical work done, which is generally it's equal to integration of PdV. One important thing is here, as we differentiate these variables, we make a cut on the head of D. This represents that Q is a path variable. On the other hand, if we differentiate these variables, we simply write dp, dv like this. And here, if you want to differentiate work done, we will write d cut w. This symbol represents that integration of dw is not equal to w. This represents that work done is an path variable. That means change of whose value only depends on the path. Let me clear that in PV diagram, if initially we are at the point A and in a process if we make our position B by this path, and on the other hand if we make this path to reach B, work done in going A to B by this path is W1 and work done for going A to B by this path is W2. As work done is an path variable, then W1 is not equal to W2. And as state variables only depend on the initial and final position, so in PV diagram, if we take a process, initially we are at the point A, and let's say for going A to B by this path, it takes T1 temperature, and let's say for going A to B by this path, it takes temperature T2, then temperature of T1 is equals temperature T2, as it depends only on the initial and final position, as in this case initial position is A and final position is B, and also for this path initial and final positions are same, as T1 is equals to T2. And in this case we can write integration of dV is equals to V, or integration of d state variable is equals to state variable, and in case of path variables is not applied. In later you will see as dq equals tds and dw equals pdv. That means integration of this is not equals dq. Integrations of dq we have to write this in terms of this, that means integration of tds, and if temperature is constant then we can write integration of dq equals to ts plus c. It shows integration of an path variables is inexact and integration of an state variable is exact, and integration of an path variable is inexact. Let's solve a problem on this topic. We have to calculate change in dp, which one is a state variable, change in dp, which one also a state variable, and we have to calculate change in work done for going A to B, for going B to C, for going C to A, and for whole cycle. Let's try to make it. At first, for this one, as it says A to B is an isothermal process, so T is constant here. T means temperature is constant. Isothermal is a process in which temperature is constant. To do this problem, and we have to know and relation between state variable, which one is for ideal gas PV equals RT for 1 mole. This is required for this problem. Here dP is equals, as final pressure is P1 and initially pressure was P2, so change in dP equals P1 minus P2. Change represents the final minus initial, so as here final is P1 and initially it was P2, so change in pressure is equals P1 minus P2. Change in volume for A to B equals, as for A to B finally volume reaches V3 and initially it was at V1, so change in volume is V3 minus V1. And dW, here initially there was no work done, so dW equals integration of P dV from initial to final. As we can see from this relation, we can write P equals RT divided by V. So we can write work done as integration of initial to final RT divided by V dV. It gives rise work done A to B, as in this case A to B is an isothermal process, so temperature is constant here, so we can get it out from the integration, and integration of 1 by V is ln V. So finally work done for going A to B is RT ln V3 by V1. For process B to C, for going B to C, change in pressure is equals, as pressure is P1, so there is no change in pressure, so change in pressure is 0. Change in volume for going B to C, as we are going B to C, so finally volume becomes V2 and initially it was V3, so change in volume is V2 minus V3. And here the work done for going B to C is integration of PdV from B to C, or work done B to C equals, as in this case pressure is constant P1, so we can write it P1 and integration of dV, and integration of dV equals to V, so work done is equals P1 V. As at the point C volume is V2 and at the point of B volume is V3, so finally work done becomes P1 V2 minus V3. In case of C to A, change in pressure, for going C to A, finally pressure becomes P2, so change in pressure is equals P2 and initially it was P1, so minus P1. Change in volume for going C to A is equals, change in volume for going C to A, final, that is V1 minus initial, that is V2, and work done for going C to A P dV is equals integration C to A. Here P is variable. In case of C to A, P is varying from P1 to P2, so we can't integrate it. So we are using the relation between state variables, that is PV equal to RT for 1 mole ideal gas. So from here P becomes RT by V, and putting the value of P here we get RT by V dV equals, as it is given C2A is an isothermal process, so T is constant here and R is also constant, so we can get it out from the integration. So finally it becomes RT C2A 1 by V dV. Finally work done from C to A is equals RT ln, here integration of dV becomes ln VA minus VC, so we can write VA divided by VC. Now finally for the cyclic process, that means for going A to B, again A to B, then B to C, then C to A, at first change in pressure for going A to A, that equals change in pressure for going A to B plus change in pressure due to B to C plus change in pressure due to C to A is equals, so it becomes P1 minus P2 plus B to C no change plus C to A. Here C to A's change in pressure is P2 minus P1. So finally it becomes 0. As you can see from here, pressure is an state variable, so in a cyclic process change in pressure is 0. Also for volume, for going A to A, it also becomes 0. You can check change in volume for going A to A is also 0, as V is a state variable which depends only on the initial and final position, as here initial and final both positions are same, so change is 0, and you will find that the work done for going A to A not equals 0. So by doing this problem, we have verified that the change in state variables only depends on initial and final position, and change in path variables depends on the path.